Very good morning to all and welcome back to our course of control system. So in the last lecture we solved some numerical on transfer function calculation. That means in the last lecture we discussed that how to obtain the transfer function of a physical system if it is represented in the form of electrical circuit. So let us try to what we can say continue our previous what we can say lecture. So let's have a circuit like this, and our objective is to find, or you can say calculate, the transfer function of the given physical system. So let us consider that we are having a circuit in which a resistor and inductor and the capacitors all are connected in parallel configuration, and to this parallel configuration we applied some input ei of t, and the value of current flowing through the circuit is I of t. And suppose here we are having some output E naught of t. So this is a first numerical of our lecture. So our objective is to what we can say obtain the transfer function of this electrical circuit. So in the last lecture I told you that we need to implement some technique in order to obtain the what we can say transfer function of any physical system if it is represented by electrical circuit. So in step number 1, first of all we need to obtain the mathematical modeling of this electrical circuit. So here we need to apply the concept of Kirchhoff's voltage law, Kirchhoff's current law, or you can say simple Ohm's law, in order to form, or in order to obtain the mathematical modeling of this circuit. Then in step number 2 we need to apply the concept of Laplace transform by assuming all initial conditions to be 0. Then in step number 3 we need to identify the what we can say input and output of this particular circuit, and in step number 4 we need to obtain the ratio of output by input. So in this what we can say circuit, it is given that the input excitation to the circuit is current I of t, and the output of the circuit is nothing but E naught of t. That means by the end of this what we can say numerical, ultimately our objective is to find the ratio of E naught of s by capital I of s, where E naught of s is nothing but the Laplace transform of output and I of s is nothing but the Laplace transform of input. So this is what our objective is. Now let us try to solve this what we can say numerical step by step. So in the numerical it is given that the input is current I of t and the output is the voltage across capacitor, which is nothing but E naught of t. So step number 1, we need to obtain the mathematical modeling of a given electrical circuit. So in order to obtain the mathematical modeling of this what we can say circuit, here we need to apply the concept of Kirchhoff's current law. So let us consider that the value of current flowing through resistor is like I R of t, the value of current flowing through inductor is I L of t, and the value of current flowing through capacitor is I C of t. So if you apply Kirchhoff's current law to above what we can say circuit, we can write here as incoming current is nothing but the outgoing current. So with respect to this particular node, because this is nothing but your single node, so with respect to this particular node, the incoming current is nothing but current I of t, and the outgoing current are the value of current flowing through resistor, value of current flowing through inductor, and the value of current flowing through capacitor. So I can write here as incoming current I of t, which is nothing but outgoing current. So I R of t plus I L of t plus I C of t. So this indicates the value of current flowing through resistor, this indicates the value of current flowing through inductor, and this indicates the value of current flowing through capacitor. Now I can write here as I of t is nothing but this IR of t is nothing but the value of current flowing through resistor. So if you apply Ohm's law, because all the elements are connected in parallel, So the value of this voltage will remain same across each element. So I can write this IR of t as EI of t whole divided by capital R. In the same way, the value of current flowing through this inductor I can write here as V equals to L di by dt to I is 1 upon L. So here 1 upon L integration 0 to t EI of t dt, because we know that voltage across inductor V is nothing but what? L di by dt. So I is nothing but 1 upon L integration 0 to t V of t dt. So the same logic we have implemented over here. So if you apply this logic, we will get this equation. In the same way, if you try to write this value of current flowing through capacitor, so it is nothing but I equals to C dV by dt. So it is nothing but C d of EI of t by dt. Let this will be your equation number 1. So equation number 1 indicate what? The integro differential equation which represent the mathematical modeling of this particular circuit. Now if you apply step number 2, what we need to do? We need to apply Laplace transform to equation number 1 by assuming all initial conditions to be 0. So if you apply Laplace transform, we can write this I of t as capital I of s, which is going to be equal to capital EI of s whole divided by capital R plus 1 upon s into L into capital EI of s plus s into C into capital EI of s. Or if you take EI of s common, I can write here as 1 upon R plus 1 upon SL plus s into C multiplied by capital EI of s, which is nothing but capital I of s. Let this is nothing but equation number 2. Now we need to apply step number 3. So in step number 3, we need to identify the input and output. So in the numerical it is given that the input to the circuit is nothing but current and the output is nothing but voltage across capacitor. But if you see the connection of what we can say component in a circuit, all are connected in parallel, and in parallel combination we know that the value of current the value of voltage will remain same. That means the same what we can say voltage is going to be appear across your output capacitor. So here the value of EI of t is exactly going to be equal to what? E naught of t. So if you take Laplace transform, I can write here as EI of s is nothing but E naught of s. So what we are going to do? We are going to replace the value of this EI of s in equation number 2 by corresponding E naught of s, because ultimately our objective is to find the ratio of output by input, and in this numerical output is defined by the voltage across capacitor. That's why we need to replace this value of voltage by output. So equation number 2 can be rewritten as I of s is nothing but 1 upon R plus 1 upon SL plus S into C whole multiplied by EI of s. Now this EI of s is replaced by E naught of s. Now this indicate the output of the system and this indicate the input of the system. Now we need to apply step number 4, where we need to take the ratio of output by input. So here the output is E naught of s and input is I of s. So if you take or if you apply step number 4, so the ratio of Laplace transform of output to Laplace transform of input, which is nothing but transfer function indicated by symbol G of s, is given by output is E naught of s whole divided by input is I of s, which is going to be equal to, if you rearrange the term, you will get this as 1 upon R plus 1 upon SL plus S into C. So this indicate the transfer function of our given what we can say physical system if it is represented in the form of electrical circuit. So if you want to draw the block diagram for this, we can write this in terms of block diagram, like we are having a system integrated by block, and inside this block we need to what we can say mention the parametric function of the system. So parametric function is nothing but the transfer function. So here 1 upon r plus 1 upon SL plus SC, this indicate the parametric function of a given system. To this we need to apply some input. The input is nothing but I of S, and we are getting some output, and the output is nothing but E naught of S. So this will be the reference input signal, and corresponding to this we are getting some controlled output signal, which is very important. So in this way we can have the flexibility to obtain the mathematical modeling of any physical system if it is represented in the electrical circuit form. Now let us try to solve one more numerical to obtain the transfer function of a system whose impulse response is available with us. So how to obtain or how to solve those type of numerical. So let us try to solve that type of numerical in which we are having the impulse response of a system, and our objective is to find its corresponding transfer function. So let us consider that example number 2 of today's lecture, in which the impulse response of the system is available with us, and the impulse response of the system is given by g of t is nothing but e to the power minus t in bracket 1 minus cos of 2t, and our objective is to obtain the transfer function. How to obtain the transfer function of given system? So कहने का मतलब है कि हमारे पास में एक व्हाट वी कैन से सिस्टम है, और वो सिस्टम को अगर आप इनपुट में इंपल्स एक्साइटेशन देते हो तो वो सिस्टम इस तरीके का आउटपुट जो है वो जनरेट करती है. Impulse response of system is nothing but what? The output generated by that particular system when it is excited by impulse input. So जब मैं उस सिस्टम को इनपुट इम्पल्स दूंगा तो वो आउटपुट क्या जनरेट करेगी, वो आउटपुट आपको गिवन है. So this indicate the impulse response of the system, and our objective is to find the transfer function. So from the knowledge of our previous lecture, I told you that in some cases transfer function is also defined as the Laplace transform of impulse response of control system. That means if you are interested to calculate the transfer function, you have to take the Laplace transform of impulse response of a given control system. So in this numerical, impulse response of control system is given to us, and our objective is to find transfer function. So from the knowledge of our previous lecture, we know that transfer function is nothing but Laplace transform of impulse response of control system. So if you have impulse response of control system, and if you take Laplace transform, or if you apply the property of Laplace transform to the impulse response of control system, ultimately whatever the mathematical equations which you are having in S domain, that equation indicate the transfer function of that particular system. So transfer function, which is nothing but capital G of S, is nothing but Laplace transform of impulse response of control system. So impulse response of control system is indicated by symbol G of t. So here what we need to do, we need to take simple Laplace transform of this equation, e to the power minus t in bracket 1 minus cos of 2t. कहने का मतलब ऐसा है कि अगर आप लैप्लास ट्रांसफॉर्म लोगे इंपल्स रिस्पांस का, तो आपको ऑटोमेटिकली उस पर्टिकुलर सिस्टम का ट्रांसफर फंक्शन मिल जाएगा. नाउ हाउ टू टेक लैप्लास ट्रांसफॉर्म? सो हियर फर्स्ट ऑफ ऑल वी नीड टू स्प्लिट दिस फंक्शन. सो इफ यू मल्टीप्लाई e to the power minus t inside the bracket, it is e to the power minus t into cos of twice t. Now what we need to do, we need to take Laplace transform of individual what we can say component. So here you need to apply the property of Laplace transform. So I am writing here transfer function like Laplace transform of e to the power minus t minus Laplace transform of e to the power minus t multiplied by cos of 2t. So here Laplace transform e to the power minus t is nothing but 1 upon s plus 1 minus Laplace transform of cos 2t. It is nothing but s upon s square plus a square, but a is nothing but 2. So s upon s square plus 2 square multiplied by e to the power minus t. Apply shifting property. So we need to replace s by s plus 1 because यहाँ minus है. So ये आएगा आपका s plus 1 whole divided by s plus 1 whole square plus a square, which is nothing but 2 square. And then if you solve this equation, you will get 1 upon s plus 1 minus s plus 1 whole divided by s plus 1 whole square plus 2 square is nothing but what? 4. So this indicate the transfer function of a system whose impulse response is known to us. So in this way we can have the flexibility to obtain the Laplace transform of a system whose impulse response is available with us. The thing is that we need to simply take the Laplace transform of impulse response of that system, which indicate the final transfer function of our system. So in this way we can have the flexibility to solve the numerical on transfer function, what we can say, approach. In the next lecture we are going to start new, what we can say, unit from our course, which is nothing but the concept of block diagram reduction technique followed by signal flow graph. Thank you.